So today, I will introduce about, my supervisor, Felicity, will introduce the diffusional thermal instability of planar and cylindrical premixed flame. And my name is Zhang Yihong. In Japanese, I have kanji shime chou iko desu. And this is master student in Graduate School of Mathematics, Kyushu University. And I will talk about the instability of cellular frames with heat loss in the framework of diffusional thermal models. Then our idea is from originally, I think, Shibasinski in 1977, and this is about without heat loss. This is an adiabatic case. And also after that, we have the other paper by Julian Clubbin in 1979. It's about with heat loss non-adiabatic case, also in the depression of thermal models. So firstly, I want to introduce about the physical model, which is simply, I think, this is a very simple chemical reaction model, which is one reactant, two reactant, and some combustion products. Then they are evaluate in the inlet gas, some inlet gas which is we call M0, and there's some M1, M2. And we suppose one of the M1 or M2 is the limited component. And so our purpose is to consider about the cellular frames stability. So we give something like this. There are formed gas and fresh gas over here, and the propagating of the flame front in this direction. Okay, and this is the flame front. So the next thing is to introduce the Gaussian equation of this model. Firstly, the first equation is about heat equation in actually from the conservation law of heat, and also the second one is concentration equation. Then, so the firstly, let's suppose the gas is dimensionless. So these two terms, this term and this term is equal to 0. Then with heat loss, there's minus this K multiple sum, this T minus TU is from the Newton's law of cooling. And this is actually it's a linear heat loss term. So this minus means if there is heat loss, the temperature will decrease. And the last term is the reaction term, which is with exothermic. This is why this is plus, not minus, right? And this small w is from Aronna's law. I wrote over here. Here, this R is the universal gas constant, and E is the activation energy. Then, okay, and okay, here this is T is temperature, and C is mass fraction. And also there are some very important variables, parameters, which is this lambda is the thermal conductivity, and this D over here, this species diffusivity CD. Okay. Then so this equation is with unit. So to convenience our study, we plan to use the dimensionless equation, which we have some change of variables or divide some units of the mass fraction with temperature over here. So by dividing some specific temperature or mass fraction, then we get the dimensionless parameters or variables over here. And we input actually from the previous page this heat loss, and we input this heat loss like H over here. This is the heat loss term. Okay, and Lewis number over here is actually we define like the conductivity, thermal conductivity over the diffusivity. Okay. Oh, sorry. Oh, one thing. This we give this small parameter, which is amplitude, I will introduce over here. This actually is this is the flame front over here. And we suppose like this is the cellular flame front, right? So we give also firstly, we have the plate zone over here, and plate zone, the length of the plate zone is about 0.4 millimeter. And over here, we give an amplitude. Actually, this is a wave. So we give the amplitude, and we suppose this V is value like this is exponential IKZ. This K is the wave number. And we also use some definition of the wave length. So they are opposite. Here, this K is wave number. And with temperature and mass fraction, we give such a expression. Okay, so by analysis, this system, we need to input this zero division number, which is equal to this, and we suppose this is much greater than 1. But actually, by Jordan Clavin or also Simasinski, they said this beta is about 16 or sometimes 20. Okay. It's not very large, but here we can suppose this is much greater than 1. Then we have such a perturbation and just expansion of the omega. Okay. After that, maybe some calculation. Then we get this right line, which is dispersion relation. And this dispersion relation is about here. There is H0, which is the heat loss term. And gamma is defined B. And for firstly, we analyze the small value of omega and K, and also with the adiabatic case, H0 equal to 0. Then we have this relation, and by with supporting something, because you calculate this as polynomial. So finally we get omega 0 is equal to K, with some function above K, and we'll draw this picture. Not the dashed line, just the solid one. This line. And we can see that there's a critical number of wave number K here. So that means if we give some L1 over here, some L1, not all the L1, just some L1 over here, then we can get this critical number. And over here, we say omega does not have positive real part, then the system remains stable. So here, in this part from 0 K, from 0 to Kc, which is unstable, and the remaining part will be stable. Okay, so to consider about the heat loss term, which is not very easy by just calculate one by one, then we consider to use the Hurwitz criterion. Here we just introduced one of the corollary of the Hurwitz criterion. So if we give the third order system with A0 is positive, this function equation, then even only this, we see this is one of the mirror of this criterion. So A1 only even only if A1 is positive, A2, A3 also positive, and this delta 2, which is A1, A2 minus A3, A0 is also all of them is positive. Then the roots of the system have negative real part, or if this is real number, it would be negative. Okay, so why we consider to input or to use this criterion? Because here we have omega over here, right? Omega is actually this power is one half. Then there's one and multiple one half, maybe 3/2. The power is 3/2. So if we give a square, then it would be third order system. So, I'm sorry. Okay. So after calculation, we get this just from originally from this relation, this first relation. Then we get this A0 from A0 to A3, and also the mirror delta 2. Okay, so previously, previous criterion says that all of them should be positive. So let's see it one by one. A1, if A1 is positive, we give this purple and the gray line. This gray line and this purple line. K and L1 should be in this region. Firstly, just between this gray line and the purple line. And for second one, A2 is positive, means this green line. All of the K0 and L1 should be greater than this green line, this real red part. Okay, for A3, this S3 means that if this is not 0, then A3 is always positive. Okay, so A3 is all right. We don't need to see that. Then finally, for delta 2, this is very interesting because we all know the result is the stable region is from the green line and between this green line and the red line. But if you use this criterion, then when K is smaller than K star, then it's all right between green line and red line. But if this K is greater than K star, then from the criterion that this part is unstable over here, because these two roots will exchange over here. This alpha 3 and alpha 2 and alpha 3. If you just compare with these two, then that is one thing that we need to test about this region. So I test. I give K is 1.45 and L1 is minus 18. Also here, then the result is giving this stable. Omega is smaller than 0. Omega is negative, so it should be stable. So we consider the reason that when we get this result, when we use the previous criterion, we have an operation that's something square. So square means one more root will come out. So this red line is that one more root come out from the operation of square. So we just throw it out. We just remain this green line and this this line. It's coefficient with it's coincide with the Sierczynski or joint clouded result. And we can also calculate this. This point is -2, and this point is about K0 is this and L1 is this very exact number. Okay, for heat loss, firstly, John Clubbing introduced one of the things about printing, and if we introduce this H, just like before. This H is over here, and we give some operation, not operation, just calculation directly. Then we can draw a picture like this. This is a figure. We can plot this figure, and we can also prove that this part from the critical number here, this region is represents H from 0 to 1. And in this part, H is greater than 1. And also, if we want some this heat loss is not positive. If the heat loss is negative, then maybe some heat from outside of the system will come in. Just I guess. Then we have such a relation. Then I consider also, if you see this line, there are two branches. The faster branch means from the critical to the adiabatic case. Then if the heat loss is decreased, it will equal to this U. This U is the flame front velocity, will equal to the U adiabatic. Okay. This line is, I think, is more useful, or we can realize in the real. So, but for the left line, it's by Julian Claudius' word, I think this is difficult to realize in the experiment. Okay. So we also use the dispersion relation. All of them come from the dispersion relation. Then with heat loss, this is H0 equal to 0. And this is H0 equal to 0 is just we introduced before. And if we give more more heat loss, then it will be like this. It will increase. And over here it will decrease. And the region of stable will decrease when heat loss is increased. So we can see that heat loss is destabilized this system. And I also consider about something more, like we give H equal to -2, something negative, and H equal to greater than unity, 1.2. Then if we see that this H2, H equal to -2, -0.2 is just parallel with the others. And also here, this one is H0 equal to -0.2. It's just something corollary from the previous result. But if H is equal to 1.2, we have this yellow line in the left and the two purple line over here. This purple line and also this purple line just directly from the dispersion relation. Then I can also test the point, because this figure is not very good, because if you draw this yellow line, then also from here, there's a small region over here. There's this line is 1.2. So we test if over here we can get one of the positive real solution of omega. So this red point are all unstable. Only in this region and also this region. This region is stable. We just test. This is minus the negative real part over here. This red point just for H equal to 1.2. We'll focus on this. Okay, I think that is something I'm now learning and studying. And thank you for listening.
私も簡単に喋るんだけど、今、質疑応答やった方が、はい、いいと思います。何でも、質問して鍛えてあげてください。皆さんよくご存知の話をね、繰り返してるだけですけど。
Did you check the imaginary part of your is it alpha? Omega.
It's omega.
So that's imaginary part.
Yeah.
When the L1 is positive,
Yes.
you get. I see.
I cannot read your figure.
Sorry.
When h equal 1.2,
Yes.
there are two purple lines.
Yes, two purple lines. Yes. Sorry.
The lower purple line doesn't divide
Yes.
stable and unstable. Both unstable.
Yes, both unstable.
Irrelevant.
Yes.
I see.
I think irrelevant is.
Both unstable.
Yes. This line does not use for it. Does not use.
This is not inconsistent with Hurwitz criterion, right?
Hurwitz, yes, I think so. But this is directly from these two lines, purple line, and also this yellow line on the left is directly from Hurwitz criterion. And if we test, then we find that it is positive.
But the qualitative nature of the eigenvalues are different because I mean the bottom this guy has positive eigenvalues but and positive real eigenvalue but the in the middle region eigenvalue includes the complex conjugate eigenvalues.
Yes, the complex.
Yeah. Is it intrinsic or to distinguish two?
If there is chance, if there is a complex number or okay, I think it's yes. I didn't consider about this. Maybe I will do this after.
Because the presence of complex conjugate eigenvalues may cause pulsating or oscillatory instability. Yeah. So it is worth checking.
Okay, thank you so much.
Yeah.
Yes, please.
Yeah, I'm not familiar with this system, but so just I have a short question that in the stable system or here, does it mean the frame is flat or the frame can be exist? Which means stable?
I think stable means this cellular structure will remain for some time. Or
if the system is unstable, so
yes.
What gonna be the?
It will be
what frame?
Because sorry. I see. So this is the propagating direction over here.
Yeah.
So in this direction. So if this system is unstable, then this point will be slow. The velocity of this point and velocity of it are different. It will be slow and this will be fast.
See.
This is something like this.
Thank you. I understand.
And also, all of the point over the point front will be different. That's I picked two examples over here.
Yeah, thank you.
Any other questions?
So can you show the map again? The L1 and A. So this one, left-hand side graph, left-hand side, what L1, this one. I mean, when H is equal to 1.2,
Yes.
so you get this line.
Yes, this yellow.
I see. And that yellow line On the right hand side.
Yeah.
No,
from here.
from there. So,
Yes.
so you have somewhere there.
Yes. This,
Overlap.
yes. This and this point. I dropped this to like they are starting.
The same point.
Yes, same point. Right.
So that
And this is like
both I see. I see.
these two pictures need to connect.
Connect. So the next one, but the not that one,
This
that
one.
that
This
point, that one. What? There's no imaginary part is zero.
I think so by yes.
Although I see. But in that region, so there may be some. So that one imaginary part is zero. There.
Yes.
The next one, right? That next right, and that one. What imagine? I mean,
Yeah.
conjugate.
Yes.
Complex.
Yes.
So there may be somewhere,
Yeah.
some borderline
Um.
from at that which imaginary part is zero, like a pulsating.
Okay.
Like I see.
I see. Okay.
So this diagram shows only real part is positive or negative.
Yes.
Unstable or stable means only you're talking about
Real part.
real part is negative or positive. So
Yes.
I see. So it may be interesting to show the borderline
The border.
between
Complex
imagine
and the real, just the real roots. I see. Thank you.
だから教科書には H が1よりも大きいところは、いわゆる物理的になんか存在ありえないってなんか大抵書いてますよね。だから誰も書いてないんです。H が0から1までがだって接続領域で、1のところでピークに、ペンチングの、ピーク。
さっきのやつが、
それを乗り越えていて、もうどの本にも、もう、現実には起こらないみたいな、そういうコメントが書いてあって、
その領域を見てるわけですね。そっちを見てるわけですね。
だから、あったらいいなと思って。
なるほど、なるほど。なんか、I asked someone, I forgot who, but some kind of combustion theory person. And I asked, is this really physically not accessible in the H greater than 1 region? And that person said, depending on the Lewis number or so, maybe depending on some kind of parameter, there may be a situation. The lower branch is stable. I don't know when, but
Okay.
somehow you may introduce some kind of parameter, then lower branch can be stable. I'm not sure.
Thank you so much.
エンカレッジング。
very, very interesting. そっち側なんですね。
So
Good job.
Thank you.
thank you so much.